You don't expect corrosion like this to occur in your car nowadays.
And you don't expect rust to have weakened the structural members to anything like this extent. Severe corrosion is fortunately now only a problem with old cars.
Thanks to years of testing like that at the Rover Group Accelerated Corrosion Facility at Gaydon, near Warwick.
In 12 gruelling weeks, the object is to make Rover's new cars rust. If they can.
Stones to chip the paintwork.
Granite dust for general abrasion.
Punishing road surfaces.
Salt spray.
And a sauna in a 100% humidity chamber at 45 degrees centigrade.
It's all designed to promote an electrochemical reaction.
Just a single drop of water on a sheet of iron. At the base and in the centre, ferrocides are being formed.
A special indicator that has been added reacts with them, giving this dark blue colour. Around the perimeter, a pink colour. The indicator has reacted with hydroxide ions.
Within this drop, an electrochemical cell has been created, but how exactly?
Well, as the iron dissolves, ferrocides are produced.
Electrons are also produced, but these are conducted away through the metal to the edge of the drop. There, these electrons become available to react with atmospheric oxygen and water to give hydroxide ions.
Next, the iron 2+ and OH- ions diffuse away from the anodic and cathodic areas of the water drop and towards each other to the point where they react and become iron 2 hydroxide.
In a third and final stage, oxygen dissolved in the water oxidizes this to a hydrated iron 3 oxide.
Rust.
Because this rust is porous and non-adherent, it does not form a protective coating on the surface.
And it doesn't stop more iron being oxidized and more holes appearing in the metal lattice.
Rust is very permeable to both air and water, and because it's about twice the volume of the iron that it has replaced, we get a flaky deposit below which the corrosion continues unhindered.
Salt water rusts iron even faster because of its higher electrical conductivity and the fact that its small, mobile chloride ions rapidly migrate towards the anodic site where, in the presence of ferrocides, they can produce hydrochloric acid, and that attacks iron very effectively.
So, to prevent all these reactions occurring, we must protect base steel from contact with water and oxygen and salt.
This Rover 600 is being completely broken up and examined for any evidence of corrosion that might lead to panel perforation or structural failure. It might be the fault of weakness in the design, the material used, or in the manufacturing process.
Yes, we've got a leak here. It looks as if the body white sealer bead is actually in the root of the bend all the way around the flange.
It's got to be put right, and accelerated corrosion testing is part of the process. Before the test, a panel was scratched like this.
For vehicles with Rover's 3-year cosmetic warranty, after 6 weeks of testing, no more than a 2mm corrosion blister is allowed to have spread from the cross scribes.
Well, that may satisfy the warranty requirement, but did the metal have to rust at all?
Here's the prototype of a bonnet panel that has been protected with a zinc coating front and back.
Not much of a corrosion blister here.
So just how does the coating protect steel? One way to coat steel with a thin layer of zinc is to use Faraday's laws and electroplating.
And that's what this production line at British Steel's Shotton Works in North Wales does. Rolled sheet steel is cleaned by a series of processes before being introduced into a continuous run of 11 zinc plating cells containing zinc salts.
Zinc supplied as an oxide is converted into zinc sulfate in a slurry with water. This plating solution, or electrolyte, is pumped to the cells continuously.
Inside each cell, the huge lead alloy electrode is the anode, and the steel passing close to this is the cathode.
Electrolytic deposition of the zinc onto the steel, on one surface or both, gives it a coating whose thickness depends on the electric current and time.
Coating thicknesses range from 2 to 10 microns, depending upon the degree of corrosion resistance required, with 6 to 8 microns being standard within the automotive industry.
But how does zinc prevent steel from rusting? Earlier we saw that corrosion occurred because iron in contact with oxygen and water produces a short-circuited electrochemical cell. Can we slow down the corrosion process?
The answer is yes, if we coat the steel with a sacrificial metal like zinc.
But we still get corrosion of the zinc. Let's scratch it and see what happens when we introduce water and oxygen to this system.
With two metals present, there is the opportunity for one of two anodic reactions to take place. Either this one
or this one. Preferentially, the latter reaction will occur, because the zinc is more electropositive than iron.
And the kinetics are favourable too. So, zinc is sacrificed in the protection of iron, and in the anodic reaction it dissolves to form the divalent zinc cation. The cathodic reaction is the same as before, but this time it occurs predominantly on the exposed steel surface.
The hydroxide ions produced combine with zinc ions to form zinc hydroxide on the zinc surface, and also to a limited extent on the exposed steel.
This is an example of galvanic corrosion.
A basic zinc carbonate is also formed by a reaction of the zinc hydroxide with carbon dioxide dissolved in the water. These corrosion products partially protect the exposed area, and the damage is partly self-healing.
But these salts only form between pH 6 and 12.5. Outside that range, the zinc is much more susceptible to corrosion.
Although it doesn't corrode anything like as fast as steel, it is attacked by acids in a crevice environment.
For instance, when two sheets are welded together. Let's explain how that can happen.
Pressing sheet steel in such a way as to eliminate the need for as many joints and spot welds as possible is obviously one way of minimizing corrosion.
It minimizes the number of crevices,